Alright team, I was tasked with the responsibility of doing a recap video for our last student mini lessons on solubility, KSP, and kinetics, but I needed to separate them into two. So I'm going to talk really fast and then you double speed me and then it's like 4 times the speed. So I'm going to start with solubility and KSP and go over some things that were not covered in the student video. Okay, I know they told us in the video about KSP, but a few things. The idea is that you're taking a solid, whether it's soluble or insoluble, and it breaks apart into the ions. One thing, when you write these reactions, you have to have the charge in the equation and in your KSP expression. So KSP is the solubility product constant. This is the solubility product constant expression. The bigger the KSP, the more soluble something is. The smaller the KSP, the less soluble. And no sneaky solids, right? So normally we do products divided by reactants, but no sneaky solids. So this guy times this guy times this guy squared because of the 2. So here's a practice problem, and we have to write the solubility product constant and solve for x, a review of equilibrium. A couple of things I noticed. So this guy breaks apart into 2 AGs and one of this CrO4 polyatomic. Notice they both have the charges. When this problem, they gave us the KSP. Notice this value is very small, which means, remember, if we do products divided by reactants, that means reactants favored at equilibrium, which also means that Ag2CrO4 solid is not very soluble. So if we looked at solubility rules, it would probably say insoluble, just based off that really, really small KSP value. So next, I'm starting with none of my products. If it were a common ion problem, we would have an initial amount of one of these, like if I was dissolving it in something with some silver, as opposed to just pure water. And we can write the KSP expression, the solubility product constant expression. KSP equals to Ag plus squared, notice the charge, and CrO4 2 minus, no exponent because it's just a 1. I'm also going to write this minus x, even though we don't care about sneaky solids. This minus x actually represents something a little more than it did in our regular equilibrium unit. So there's that minus x again. Again, it's going to represent something, but we can fill out our ice table. I know I'm going to add 2x of this and add x of this because we always move towards the zeros. So I'm adding these guys. And we know that I plus c, so I plus c equals e, so 0 plus 2x is 2x, 0 plus x is x. And now we can plug in and solve for x. So we have 2x and x. Don't forget this 2x goes in where it's squared. So at equilibrium, we have 2x squared times x, and that equals our KSP. Now we can do some math. So this is what we had before. I plug in, I solve. So 2x squared times x is 4x cubed, divide by 4, cube root both sides, and we get x. Notice x has a value here, or a unit here, mole per liter, or capital M for molarity. And remember, I told you that x means something. So in KSP, x is the molar solubility, which is the minimum molarity to be saturated. So Ag2CrO4 solid has a molar solubility, a minus x, of 8.7 times 10 to the negative 5th under these conditions, so under this temperature and when it's in pure water. So a small x is low solubility, a big X is high solubility. So we start with some amount of the solid, right? Did I care about it? No. So we start with some amount right here. So some number. Sometimes they tell it to you. Usually they don't because it doesn't matter. If they tell it to you, it's because they're rude and they want to mess you up. We're going to use some of it to dissolve. A tiny, tiny amount will dissolve, minus X. However much dissolves, that's the molar solubility. So minus X is the molar solubility. I can also plug that x value in. So if they ask for molar solubility, they're just asking for that x. But they could also say how much Ag would there be when it's saturated or at equilibrium. That's 2 times x. So plug that in. How much CrO4 2 minus? That's this x. Plug it in. So just like in equilibrium, you can plug in x to find equilibrium or saturated concentrations. But more often, they're going to ask for molar solubility, which is just once you have x, you're done. Sometimes they will this is just the same. So here's a practice problem. Solve for x, find the molar solubility. Sorry, I thought it was an opposite one, but same idea. All right, another piece that I knew I needed to cover, not highlighted in the videos, which they didn't have to cover, was comparing solubilities. So you can compare salts, you can compare KSPs if they produce the same number of ions. For example, that's not what I want. Let's do CaF2. That breaks into Ca2 plus and 2F minus. So that's 3 ions with BaI2. Also 3 ions, right? 1 barium, 2 iodines. So I can compare those directly. Large KSP, more soluble, meaning it dissolves into the ions more. Small KSP, less soluble. It doesn't dissolve. It favors more the solid. What if they don't produce the same number of ions? So what if I have CaF2 and then I have NaF? So this is just 2 ions. Then we have to solve for X. You can compare molar solubilities, X directly, if they do not break into the same number of ions. So then we compare X. Most soluble will have the bigger X, least soluble, smaller X. So here's an example of that. Write the reaction, write the KSP, and rank from least soluble to most. I'm going to see that they don't break into the same number of ions. So we have 3 ions, 2 of the Fs, 1 of this guy. We have 2 ions, 1 polyatomic, 1 calcium, and we have 4 ions. So I break them into the ions, right? Break, 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 break. 1, 2, 3. Okay, and then we write our KSP expression. Remember, if there's a coefficient, that becomes the exponent. And then the idea here is you can set up an ICE table and solve. We know what KSP is, solve for X, and we can compare the X values directly. So in all of these, I did an ICE table, solve for X, and now I can compare the X values, -3rd, -5th, -9th. So the most soluble is going to be the one to the -3rd. The least soluble is going to be the one to the -9th. In the equilibrium lesson, we talked about Q versus K, and they talked about QSP versus KSP, but I also want to just kind of talk about vocab. If we are at equilibrium, so Q is equal to K, they're going to say we are saturated. So in KSP problem, saturated is the same thing as your equilibrium. If they say something like we're going to shift towards the right, that means something is going to dissolve. If we shift towards the reactants, that means a precipitate is going to form. So in an equilibrium unit, they might say, which way will the reaction shift? In a KSP unit, they're going to say, will a precipitate form, which is just a fancy way of saying, will it shift left? So you're still doing Q versus K, but instead of saying which way do we shift, they will say, will a precipitate form, which is translated as, will we shift to the left? Compare Q and K. And then lastly, we had a lab this unit, so I want to look at that. All right, this lab was your very, very first titration. So here's kind of how it looks. I gave you like oversaturated CaOH2, so meaning like there were chunks. So I tried to dissolve some in the beaker, and then I put more than could actually dissolve, so a precipitate formed, right? So we shifted left, and we had this solid. Well, I wanted you to have it perfectly saturated. So you actually got a funnel, and you filtered this stuff so that what you got was perfectly saturated, meaning we were perfectly at K. We were at equilibrium. So if we have our ICE table, we started with none, plus X, plus 2X. You were at X and 2X. And then we took that and we put it in the burette. So we know that this is perfectly at equilibrium. You had acid in the flask below at a known concentration. So actually you had to do a little work. I gave you the acid and made you dilute it, M1V1, just for the practice. And then we could figure out how many moles of acid were in the flask. And then you did your very first titration. So we look for the color change. And we know that if I know the molarity of this, if I know the moles of H plus in the flask, then I know how much CaOH2 is in the burette. So you found how much CaOH2 reacted because of the 2-to-1 stoichiometry ratio, so 2 HCl to 1 calcium hydroxide. And then we could find moles of OH. For every 1 mole of calcium hydroxide, there were 2 moles of OH. So essentially then, I know moles of OH, I know how much it took from start to finish to do the titration, so I know the molarity of OH minus, which means at saturation, at equilibrium, you knew what 2X was. So then we know that if I cut that in half, I will know the concentration of calcium, and we can plug both of those numbers into our KSP. and then you compared it to the textbook. So essentially you use a titration, a known HCl, to find the known amount of hydroxide in this equilibrium, and then you were able to cut it in half to find calcium, plug into KSP. Hopefully that helps with KSP and in addition to the student video.